Welcome to this new episode of the arXiv paper pitch. This time I'm going to talk about quantum uncertainties of static spherically symmetric spacetimes. My name is Benjamin Koch, and this work has been done in collaboration with Ali Rehaninia, PhD candidate. We want to thank all these people who contributed by their comments and remarks to our work. So let's get started by motivation, and the motivation will come from time in the context of quantum gravity. So on the one hand side, we have quantum mechanics. Here we see Mr. Heisenberg. And this canonical quantization is formulated on a hypersurface of constant time, such as, for example, the commutation relations are valid on this hypersurface, and that is crucial for the theory. So there's a universal equal time hypersurface for the quantization. In contrast to that, here we see Mr. Einstein. In the theory of general relativity, time is just another coordinate of the curved space-time overall. So how do we make sense of these two clashing concepts? Well, people have thought a lot about that. And one outcome of this, for example, is the famous Wheeler-DeWitt equation. But there are many subtleties and unresolved issues within this context. Let's list a few of them. For example, there's a vanishing Hamiltonian. We have to make sense of that. You have to understand what the wave function of the universe psi actually is. There's this famous non-renormalizability of quantum gravity. There's this problem of formulating diffeomorphism invariant observables, and so on and so forth. So our ansatz for tackling this problem or contributing to this problem was to think of a physical quantization hypersurface, which is not equal time. And the simplest system we could come up with is spherical symmetry in a static spacetime. For spherical symmetry, you can, for example, use the coordinates of Schwarzschild geometry, t, r, theta, and phi. So if you impose the symmetry, of course, the functions you have in your line element will only depend on r, not on t and the angles. So you can write on an action, the Einstein-Hilbert action of general relativity, which contains a cosmological constant term, Ricci scalar, and Newton's coupling. And the metric line element you can write as a function of two free functions, which will be the fields n and g. And so now we can define the surface with equal radius, and the acronym for this will be SER. This will be our quantization hypersurface now. And then once we have defined the hypersurface, we can let go the machinery of canonical quantization on this hypersurface. And it seems to work out quite nicely, because once we have the action, we can write down the Hamiltonian, and the Hamiltonian does not vanish for this case. And it will be a function of two fields, n and g, and their associated canonical momenta, as we can see here. Now, from the classical theory, where we can write down our Poisson brackets, we do the quantization and write down commutators. And so we have a theory of quantum operators, G hat and N hat, and their associated canonical momenta. There's a little subtlety concerning the constraints, but after tackling this problem, we're still left with one physical degree of freedom. So everything seems to work. So what does that mean? We have a quantum gravity where all works. Well, there's certain things that we can do with it now, and that's what we're going to show now. So for example, we can write down the Heisenberg equation of motion for any operator with this symmetry, which we have shown here, and this is the Heisenberg equation of motion. And it's also valid for the expectation values of these operators. We can further take two operators, check whether they commute or not, and if they do not commute, they have automatically an uncertainty relation associated to them. For example, this one here, between G and P. So results of this. So if we calculate the vacuum expectation value of simple operators, we can, for example, recover the classical solution. We can also see that the classical solution for spherical symmetry has one integration constant, which is basically the black hole mass, m0. You can also calculate the expectation values of less trivial operators, and you have more additional integration constants, which you have then to identify the wave function of the given state of spacetime. As mentioned, there are the uncertainty relations, and we calculated two straightforward examples. The first example was between G and its associated momentum, and what we find is a natural formulation of the Hawking temperature. If you take the next less trivial commutator, you get a limit on this integration constant what we have shown before, and there's an upper limit and a lower limit for the theory to be consistent. So let's look in this a little bit more detail. Upper limit and lower limit. Now we show the formula. So m naught squared has to be smaller than 1 over g squared lambda and larger than this expression here on the left-hand side. The integration constants c tilde and gamma, let's assume they're of order 1. Now, everything else are just fundamental constants. So the mass of a quantum black hole is limited by two functions of fundamental constants, lambda and g basically, including h bar and c. So let's plug in the numbers because we know the values of lambda and g in our universe. And what we find is 10 to the 32 kilogram as lower limit and 10 to the 53 kilogram as upper limit. The lower limit is actually remarkably close to the Tolman-Oppenheimer-Volkov limit, which is a limit for the minimal mass a black hole should have if it results from a collapse of a star. So this is an interesting result. So let's look at the upper limit. What could be the maximal mass of such a black hole? Well, it turns out that all the matter of the visible universe has actually 10 to the 53 kilogram. So point on to the upper limit we have found here. This can hardly be a coincidence, but we don't know actually what is the deeper meaning of that. But okay, that's what research is about, so we want to find out in a later work. So let's conclude. What we did, we imposed a new quantization hypersurface, which we called static equal radius. We could do quantum gravity on the surface. We can calculate space-time vacuum expectation values, recover classical limits, but also calculate space-time uncertainty relations, which are new. And one interesting and intriguing result of that is we obtained an upper and lower limit for the allowed mass in such a system. So this is all. Please stay tuned. More details you will find in the paper. And thanks for your time and listening.